In 1984, the computer scientist Edsger Dijkstra observed that asking whether a computer can think is as useful as asking whether a submarine can swim. We are currently fixated on that analogy. As artificial intelligence becomes more capable, a specific type of skepticism has emerged, one dedicated to proving that machines possess no genuine intellect. The argument is that large language models are mathematically hollow. Critics describe them as statistical engines that use next token prediction to mimic language without ever understanding the concepts behind the words. This critique relies on a reductive logic that, if applied to ourselves, makes the human mind look equally hollow. Human consciousness is often described through its physical substrate, sodium and potassium ions trading places across a cell membrane. These electrochemical signals fire blindly in the dark, yet we perceive the result as a coherent internal life. Reducing a system to its smallest physical components often obscures the function of the whole. To evaluate cognition, whether biological or artificial, we have to look at the complexity of the output, rather than focusing solely on the raw materials of the input. The autocomplete label is a holdover from an era of sequential processing, where models guessed the next word based strictly on the words that came immediately before it. This is the transformer architecture. It dispensed with that rigid word-by-word progression in favor of a system that evaluates an entire block of text simultaneously. The core of this shift is multi-head attention. This mechanism allows the model to draw global dependencies across all data in a sequence at once, weighing the relationship between every word regardless of the distance between them. Because the model can attend to different representation subspaces, like grammar, tone, and logic, all at the same time, it maintains a massive interconnected state of the entire context. This math produces a multidimensional map of how words relate to one another within a sentence. The process generates a structural representation of the information that moves beyond simple linear probability. We see the impact of this structure in a phenomenon called grokking. It occurs when a neural network moves past simple data memorization and discovers the underlying rules that govern the information. This chart tracks a network learning modular division. In the early stages of training, the red line spikes to 100% accuracy. The model has memorized the training set, but it cannot solve new problems. The green validation line, the test for actual understanding, stays at 0. But if the optimization continues for thousands of additional steps, the green line makes a sudden vertical climb. The model hasn't just seen more data. It has uncovered the abstract mathematical rules required to solve equations it has never encountered. This leap toward generalization mirrors the way our own brains resolve the world around us. Our visual cortex follows the Bayesian brain hypothesis, constantly filtering a chaotic blur of light and noise into predictive models. Our minds ignore the irrelevant frequencies until a sharp, recognizable object snaps into focus. In both the artificial network and the biological brain, the goal is to find the signal within the noise. By minimizing prediction error, these systems move past individual data points to grasp the abstract logic that connects them, suggesting that rule discovery is a fundamental requirement for intelligence. To resolve the tension between man and machine, we have to distinguish between what a system does and what it is made of. A neural network is not a human mind. It lacks our billion-year evolutionary history and the chemical drives that dictate our survival. But return to Dijkstra's submarine. It is a cold, mechanical object. It possesses no fins, no gills, and no biological instinct to migrate. These absences do not change the fact that the vessel navigates the deep. Its lack of biological swimming equipment does not invalidate its movement through the water. Exactly the same is true for cognition. The fact that a machine arrives at an inference through silicon and copper doesn't make that inference less real. There is no magic in biological tissue and no magic in a server rack. If we want to understand the future of intelligence, we have to stop defining real thinking by the substrate it happens to run on.